Welcome back to the BcT training course. This is a continuation of Module 4. This portion of Module 4 is Session 3, which focuses on the output from the BcT and interpretation of those outputs. We will use screenshots of the BcT software to overview the outcomes. As noted earlier for Module 4, a demonstration is included at the end of Session 4 that ties all of the screens together. There are 7 learning outcomes for Module 4, Session 3, which include to list the output parameters from the BcT, to list the parameters to judge whether the results are acceptable, to determine if the back-calculated moduli are acceptable, to determine if there are potential layer compensating errors and if there are, what to do with them, to adjust the inputs to reduce the RMSE, COV, and eliminate potential layer compensating errors, to define load transfer efficiency and its use in ME design, and finally, to define potential loss of support and its use in ME design. Referring back to the flowchart included in Session 1, which introduced the guided process for back calculation using the BcT, the previous session focused on the first 4 steps. So, Session 3 focuses on and overviews the next 2 steps in the guided process, Step 5 on back calculation and Step 6 on the physical features. In terms of the flowchart, this includes the back-calculated elastic layer modulus and other outcomes from the program and answering the question, are the results acceptable? The next topic within this session is the back calculation steps. This is Step 5 in the guided process, and the screen for back calculation is shown on the slide. The purpose of the back calculation step is to have the program back calculate the elastic layer modulus for each layer within each segment. There are 4 items covered under Step 5 of the guided process: sensor acceptance for back calculation, normalization temperature for the asphalt layers, back calculation results and outcomes, and assessing the results. The first 2 items of sensor acceptance and normalization temperature for the asphalt layers of Step 5 are covered in the next slide. The user needs to make 2 decisions on this screen. The first is related to the sensors to be used for back calculation, and the second is to determine whether the asphalt elastic layer modulus is going to be adjusted to a standard reference temperature. First, the deflections recorded by the sensors are checked on the screen. Any sensor that should not be used or excluded from the back calculation process needs to be unchecked. Unchecking the box for a sensor means the deflections for that sensor are not going to be used for the back calculation process. Sensors that should not be used for back calculation are those with a negative x-axis value for the load transfer efficiency. Second, to manually enter the reference temperature when all asphalt elastic layer moduli are needed to be adjusted to that reference temperature. Simply check the box and enter the reference temperature. If temperatures are not included in the deflection file, it is suggested this feature not be used. After the 2 decisions are made, the user simply clicks the Back Calculate button and the BcT starts the back calculation process for all pavement layers and segments. The results of the back calculation process is the topic of this session within Module 4. The next topic within this session is back calculation, results or outcomes. The items covered in this part are listed on the slide and include layered elastic modulus values, relationship between modulus of unbound layers, depth of bedrock if present. This is a screenshot of the outcome from the back calculation of elastic layer modulus. We will define and overview the information included on this screen. First, the results or outcomes are summarized for each segment. The user simply clicks on the drop-down arrow for when more than one back calculation segment was defined during the final segmentation step. The outcomes for each segment are included in the tabs identified on the screenshot. There are 3 tabs, which include modulus, layer compensation, and bedrock. When the outcomes are summarized, the modulus information is always shown first. Information or the modulus results includes 2 graphs of values for the specific segment. The first is a graph of the back calculated elastic layer modulus for each layer in the structure simulation along the segment. The graph appears as an arithmetic plot, but the user can change the arithmetic plot to a semi-log plot, which is shown on the screenshot. The pavement structure used in this simulation or example included an asphalt-wearing surface, a PCC fractured slab, a granular subbase, a subgrade layer, and bedrock. The user also has the capability to turn off the results for any layer. One reason for turning off the results for a different layer is when a layer is designated as a fixed layer and the elastic layer moduli are not calculated from the deflection basins. As an example, bedrock and a thin layer as defined previously. The second is a graph of the root mean squared error, or RMSE, for each deflection point or location. The RMSE is a measure of how well the calculated deflection basins fit the measured deflection basins. The lower the RMSE, the better or closer between the calculated and measured deflection basins. The maximum RMSE value that appears in the box is 100%, just to ensure all of the deflection locations are included on the screen. The user can reduce the maximum RMSE to a specific value. It is generally suggested that 5% be used in summarizing the results going forward. A large RMSE does not imply the results are bad. It just means the calculated and measured deflection basins are different. If many of the locations have high RMSE values, say exceeding 10%, that usually implies the pavement structure needs to be revised or the layer thicknesses could be different, or possibly the elastic layer moduli exceed the minimum or maximum elastic layer modulus set by the user in the structure definition screen or step. Now let's take a look at the Layer Compensation tab. The Layer Compensation tab provides the user with information about the results. In other words, to answer the question, do we have potential layer compensation errors included in the results or back-calculated elastic layer moduli? First, let's define layer compensation errors. Layer compensation applies to adjacent unbound layers. Compensating errors can occur when the BcT is trying to minimize the RMSC or local error, but the elastic layer modulus of one unbound layer increases with a corresponding decrease in the adjacent unbound layer to compensate for the error or differences. It's highly unlikely, but not impossible, for the modulus of an unbound layer to be inversely proportional to the elastic modulus of an adjacent unbound layer. It is more likely the modulus of adjacent unbound layers will be totally independent or proportional to one another. The graphs included under this tab, Layer Compensation, is for all adjacent unbound layers. If 3 unbound layers are included in the structure definition, then there will be 2 sets of graphs, one comparing the elastic moduli for unbound layer 1 to unbound layer 2, and one comparing the elastic layer moduli for unbound layer 2 to unbound layer 3. For this example, the x-axis is the back-calculated elastic layer modulus for the upper subgrade layer, and the y-axis is the back-calculated elastic layer modulus for the lower subgrade layer. If 3 unbound layers are included and there is no fixed modulus or thin layer, the user simply clicks the forward or backward buttons on the screen to see and review each graph. Now let's overview how to identify when compensating errors may exist between 2 adjacent layers. The 2 variables for making that decision are the R-square value and the slope of the relationship as shown on the screen. If the slope is positive, as in this case a positive 0.12, it is expended that no compensating errors are included, so the results are acceptable. The R-squared term is not needed. If the slope is negative, however, then the R-squared terms need to be reviewed to determine if the back-calculated elastic layer moduli are inversely proportional. There is no hard value to always identify that 2 elastic layer moduli of adjacent unbound layers are inversely proportional. A value of 0.3 is suggested. If an R-squared value of 0.2 to 0.3 or higher is reported, the user is encouraged to try and reduce it further by considering combining layers or fixing one of the adjacent layers, making sure one is not responding as a thin layer. As a reminder, the back-calculated elastic modulus can be inversely proportional, but it is not likely because as the layers dry out or increase in moisture content, the layers will both increase or decrease or be independent, as illustrated in the example. Now, let's review the Bedrock tab. The Bedrock tab provides the user with information about the subgrade thickness and depth to bedrock. The x-axis is the station distance, and the y-axis is the depth to bedrock, or the thickness of the subgrade or lower subgrade layer above the bedrock layer. As illustrated in this example, the depth to bedrock or subgrade layer thickness can be highly variable. In this case, the variation in the subgrade thickness is the rock outcroppings that vary along the project. The results that are reported in the summary of results or the next session of Module 4 represent the average layer thickness of the subgrade and average back-calculated elastic layer modulus of the subgrade. Layer thicknesses or depths that approach 600 inches are representative of responses without any bedrock layer. The user needs to make a decision on whether a bedrock layer is present through the entire segment or not. The next topic within this session is assessing the results from the back calculation process. There are 4 items in assessing the results from back calculation. They are hitting the upper or lower limits placed on the elastic layer modulus values from the structure definition step, RMSE or root mean squared error values, compensating layer errors that was defined and discussed in the previous session, and coefficient of variation that will be covered in the summary section of this module. So, the first 3 items will be discussed in the following 3 slides, and the coefficient of variation will be presented in the next session. The first assessment is to review and ensure we are not hitting an upper or lower limit of the elastic layer modulus values. When the back-calculated elastic layer moduli hit one of the limits, the RMSE values are usually much higher compared to those without hitting the modulus limits as shown in the example. When the limits are hit or encountered, increase the limits unless that increase does not make engineering or practical sense. The second assessment is to review the magnitude of the RMSE values and consider removing the higher values. The BcT program uses a maximum threshold default RMSE value of 100, so all values are included in the plot shown on the screenshot, but the user can and should reduce that value. A threshold RMSE value of 5% is suggested and was determined based on comparing the results to determine the upper RMSE, where the average back-calculated elastic layer modulus did not change much with threshold RMSE values lower than 5%. Values above the RMSE threshold value entered by the user are excluded from calculating the average back-calculated elastic layer moduli. Layer compensating errors was defined and discussed in an earlier portion of this session, so we will only hit the highlights as a reminder. Layer compensating errors is the relationship between 2 adjacent unbound layers when the back-calculated elastic layer modulus are inversely proportional. In other words, a negative slope between the modulus of adjacent unbound layers. Layer compensating errors are typical when one of the unbound layers is considered a thin layer and the BcT is trying to calculate the elastic modulus of a layer when the deflection basin is basically independent of the stiffness compared to the other layers. Compensating errors are defined as a negative slope with the R-squared terms more than 0.3. If compensating errors are defined, normally the pavement structure needs to be revised by fixing the modulus of an unbound layer or separating other layers. The next topic within this session is Step 6, or the physical features from the back calculation process. 2 parameters will be addressed under this topic: load transfer efficiency of transverse cracks and joints, and loss of support or potential voids or material disintegration of the bound layers. Let's start with load transfer efficiency. Load transfer efficiency is defined and explained in Chapter 4 of the BcT User or Help Manual. Different procedures have been used to estimate the load transfer efficiency across joints in PCC pavements. Within the LTPP program, the load transfer efficiency of transverse joints were measured for jointed plain concrete pavements and is calculated by the equation shown on the slide. Basically, the deflection measured by the trailing sensor on the opposite side of the transverse joint, and typically 12 inches from the center of the loading plate, is divided by the deflection measured by sensor in the loading plate to determine the load transfer efficiency. For flexible pavements, different sensors have been used because the basins are different from PCC pavements, especially in the summer when the elastic modulus of the asphalt is much lower. The LTPP-PCC equation has been used by some agencies, but the one suggested for flexible pavement is shown on the slide. Basically, the deflection measured by the trailing sensor on the opposite side of the transverse crack and typically 12 inches from the center of the loading plate, is divided by the first sensor from the loading plate on the other side of the transverse crack, typically 8 inches from the center of the loading plate. The user first selects the sensors to be used in calculating the load transfer efficiency across the transverse joints of PCC pavements and transverse cracks in flexible pavements. Using the LTPP definition of load transfer efficiency from the previous slides is shown on the screen. The deflection measured at sensor 9 is divided by the deflection measured by sensor 1, or the sensor under the load plate. The spacing and sensor locations are shown on the slide for the example. The trailing sensor is sensor 9 and sensor 1 is under the loading plate. For flexible pavements, the trailing sensor or sensor 9 that measured the deflection is divided by the deflection measured by sensor 2, or 8 inches in front of the center of the load plate. The estimated load transfer efficiency using both equations are shown for the same segment. For PCC pavements, the LTPP equation is suggested for use, but for flexible pavements, a different sensor on the load side of the transverse cracks is suggested for use. The BcT program will use all drop height or target loads for load transfer efficiency, but the user can select just one or all of the target loads. The test type used for load transfer efficiency should only be those test locations across the transverse joint or crack, in this case, test type 1. The deflection basins measured across the transverse joints and cracks should not be used for general back calculation of elastic layer moduli. Next is the loss of support or void detection potential. This graph illustrates the determination of the loss of support variable, which is in accordance with the 1993 AASHTO procedure. Chapter 4 of the BcT User or Help Manual includes discussion on the loss of support variable. In summary, the loss of support variable is the intercept between the deflection versus load level relationship. Positive values above a certain magnitude suggest potential voids beneath the PCC layer. However, this variable can be used to visually determine how the loss of support variables change along the segment. Positive and negative values can suggest anomalies or disintegration of mixtures or materials beneath the wearing surface. This slide includes a screenshot from the loss of support index along a flexible pavement segment. As mentioned on the previous slide, the loss of support can be used to identify areas where the deflection versus load is changing along the project segment. This loss of support index can be used to strategically locate where to drill cores for confirming what is changing along the segment. In summary, the loss of support index can be used to estimate whether there is potential for anomalies and disintegration of mixtures and materials below the surface. This ends Module 4, Session 3. The next module of the training course is Module 4, Session 4, Results for Rehabilitation Design.